So if we take a look at D, we've got 3 parts. So we want to go through and initiate our process and try and come up with how we can go through and solve all this. So let's start with part A, or question A. What are we being asked to solve for? Okay, I prefer the abbreviation MLC. And then oxygen, since we aren't saying atoms of oxygen, we're immediately going with O2. What are we starting with? What are we given? One molecule of nitrogen dioxide. So we could go through and we could start with, provide a little bit more space on this, 1 molecule of our nitrogen dioxide. Note within that, we've got a little bit of nomenclature that you're responsible for, so you can go through and process that. We're placing that 1 molecule of nitrogen dioxide in the numerator. So on top, why? Why not place it in the denominator? The quote-unquote measurement unit that we're using in this case would be molecule. Molecule is in the numerator in our answer. Let's keep it in the numerator in our work. All right, and try and follow that logic through. All right, so molecules of nitrogen dioxide are not the same thing as molecules of oxygen. So what do I need to do? I need a conversion. Okay, in that conversion, I already heard someone say I wanted to cancel molecules of the nitrogen dioxide. Okay, and you'll note, I'm not specifying a number, okay, and I can't reiterate this enough. Okay, as I work through any kind of conversion process with any student from any class, everybody wants to put in a number. We don't know what number to put in yet. Okay, so don't put in a number. All right, the molecules of nitrogen dioxide must cancel. What do I want to convert to? Molecules of oxygen. All right. So now we get the fun question of, does this conversion factor exist? All right. And this one does become a little bit challenging, and some people might kind of back away from it. Okay. And that's probably because of what you've memorized on where this conversion factor is found. Okay. And since you're a little bit hesitant or nervous about that, let's just say, okay, I don't know. I don't know what that conversion factor is. Okay? And if we don't know, what should we do on the exam? Move on. So go to the next part of the question. What are you being asked to solve for? We want moles of oxygen. What are we being asked to start with? Moles of nitrogen. Whoops. Oh, that was a typo. That should say dioxide. And I think it needs to say dioxide, so we'll keep that fixed in there. So moles of nitrogen dioxide. We'll place that again in the numerator. Why do we want it in the numerator? The measurement unit is moles. That's the measurement unit I want for my answer. And of course I missed. Okay, in my answer I've got moles in the numerator, so I'm going to keep moles in my numerator in my solve. Are those two things equal to each other? Should have been a no. Moles of nitrogen dioxide are not the same thing as moles of oxygen, so what must happen to the moles of nitrogen dioxide? It has to cancel out, which means that unit has to appear in the denominator. What do I want to appear in the numerator? Moles of oxygen. Do you know where this conversion factor exists? Right. Admittedly, the molecule one, I only saw one person respond or even acknowledge that question, and they made a face. Okay? I don't know about that one. So I was looking at them, hoping to see that we saw a different response when we looked at this moles one, and instead of getting a different response, I did get a different response, but it was back to the non-existent response that most people give me when talking through this. Okay. So if we're looking at this, moles to moles comes from our balanced chemical equation. So we could go back up to our chemical equation and say, oh, there aren't any numbers there, so it must be 1-to-1. Nope. We have to make sure we balance it, so we should go through and ensure that our equation is balanced. It's a relatively short equation, okay, with the intent being that it's going to be easier to deal with, to go through and balance. Admittedly, this one is a little bit trickier, but we're going to get 2 and 2, and then we should get 1 for our oxygen. Did I do that math right? Okay. So what does that mean? We can now pull our coefficients, the relevant coefficients, out of the expression. Okay. The moles of oxygen we can say is 1. The moles of our nitrogen dioxide we could say is 2. So even if we didn't have the typo, it would still technically work for this question. We'll talk about why in a second. We can now punch it into the calculator, and what do we get for our answer? 0.5. We should get 0.5 moles of oxygen gas. Cool. We've now gone through and solved part B. We didn't like part A, but maybe we didn't have to worry about part A. We just lose those points and we move on. Then we go back and see question C. Why is the numerical answer to question A invalid, but the numerical answer to question B valid? This is problematic because this means we need to know what A was. Okay? So we now got to go back to A and say, okay, what's going on within this? Okay? Where do we find the conversion factor that relates molecules of one substance to the molecules of another substance? Okay. There was enough silence, yes. There's enough silence that what we're going to do is, instead of looking at molecules, we're going to go back to the one that theoretically we understand a little bit better. Let's get rid of C so it's out of the way there. We'll go back to this one, and we said that came from the balanced chemical equation. Okay. When we initially brought in moles, we actually talked about the complete unit. Okay. And we stopped writing out the complete unit because the complete unit was absurdly long. Okay. What was the complete unit? Okay, let's just look at this one here. What's the complete unit for our moles of NO2? It's moles of molecules of NO2. Why is that particularly interesting or a value to me? If we look at our expression up here and we say moles of molecules, trust me, of oxygen, what could we end up dropping from our expression? Mathematically, it doesn't work like this, but the moles can drop from our expression. Remember, chemical equations, first and foremost, gave us information about the number of molecules. That's what they do. What we decided was the number of molecules was a nonsense unit to use because we can't grab a single molecule. We can't measure a single molecule. So what we need to do is scale the number of molecules up to a massive number so that we can now measure that amount. That was the point of moles. Which means, when we double back to question A, where do I find the conversion factor between molecules of oxygen and the molecules of NO2? The balanced chemical equation. It's the exact same location. Okay? All that's happening is a slightly different nuance or interpretation of the unit we're pulling out of the chemical equation. Instead of looking at a massive number of them, we're just going to look at 2 molecules. Right, which means we can again use our chemical equation, pull the coefficients directly out. We have that 2, we have that 1. And what would we get for answer choice A? 0.5. Numerically exactly the same. 0.5, what was our unit? Molecules of O2. Mathematically, everything holds water. Everything's perfect and happy and exciting. Okay. But now we get, as I start to erase the wrong part. Question C comes in and rocks the boat a little bit, because what question C is now asking you to do is to think critically about the numerical answers you just provided. We're saying the numerical answer to A actually makes no physical sense. It is invalid. But the answer to B is actually okay. They're the same flippin' number. Why is that different? I'm not allowed to have half of a molecule. Can I have half of a massive number of molecules? Yes. Okay? There's very few ways that we can actually probe your understanding of moles. And guess what this question is? That way. It's actually asking, do you understand what it means to reference moles? Okay? Versus molecules. That's the point of this question, is it's actually drilling into the meaning of the unit that we're dealing with. That's it. The numerics all come out the same, our conversions all come out the same, but it's now actually asking, can I have those things in reality? That's it. Does that make sense? You good with that, Marcy? Questions about that or anything else? 19, 13, 19. I would argue, is moving into stuff that I think is really important that is actually chemistry related. And I'm a little nervous about the content for it, but I keep going back and checking it, and I'm pretty sure it does actually show up in the lectures. So we're actually okay in that respect. What we're trying to discuss is what connection, what kind of relationship do we have between the salt that's dissociating into our water and the water molecules themselves. So if we were to go through and look at sodium bromide as a solid, when I add it to water, that's going to turn into the ions. Sodium ion aqueous plus bromide ion aqueous. Okay, that aqueous means that the ion is dissolved in water. Well, what does that mean? What would that actually look like when we talk about it being dissolved in water? So let's just look at the sodium. So we're going to have sodium floating around as an ion. Relatively straight, it's just going to be a circle. Okay? In fact, we could just mimic that. We just say sodium, cool, circle. That's our sodium, and we know it's positively charged, so we can draw the positive in the middle of it. If we were to now consider what water looked like. Water has the formula H2O, and since we were good at drawing Lewis structures, we could now go through and draw our water molecule, and water would have our oxygen as that center atom with its pair of electrons, and then that would get connected out to the hydrogen atoms, without pairs of electrons. The shape that we'd get out of this would be bent. We know it's bent because it has 4 groups of electrons. Of those 4 groups, 2 are bonds and 2 are non-bonds, and that means the shape that we get is bent. So we're now actually looking at a representation of the molecule of water. Okay. Does it matter? I don't know if I can pull this off. I'm going to try it. Ooh, I can't. Does it matter the orientation? Whoops. Of my water molecule? Is that a better orientation? Is that a better orientation? Is that a better orientation? Sorry if it's changing sizes. How do we know? Okay. The way we know is going to be evaluating the balance of charge within those individual species. When we look at the compound of sodium bromide, would we expect sodium ions to get near each other? Why not? They're both positive, and like charges repel. Did we learn that already? Yeah, when did we learn that? Atomic structure. Okay. When we build out atoms, we put more protons in, they would repel away from each other, and that would mean we don't get anything other than hydrogen, except what else did we add? Neutrons that kept those protons together. Okay, so atomic theory already explains some of this. So we wouldn't expect a bunch of sodiums to get near each other because they're all positively charged. Okay? If we're going to bring in the water molecule, we want to understand how the water molecule would interact with that positive charge. And if we think about it, we go, oh, well, it's just the charge. Well, what charge appears in the water molecule? And that's technically a harder question because we haven't talked about formal charge, right, on an individual atom, but we have talked about it on a molecule. Is the water molecule formally charged? No. How do we know? The upper right-hand corner of the formula for water, when we look at that upper right-hand corner, there's nothing written there, which means its formal charge is 0. Okay? So there is no formal negative or formal positive in water. Okay? Does that mean it doesn't generate some partial charge? Okay? That partial charge is now going to come down to the individual characteristics of the atoms making up those bonds. Okay? What's the important characteristic of those atoms? It's a really big word. Electronegativity. The concept that helped us to explain whether we had an ionic bond or a covalent bond or a polar covalent. We haven't talked about polar covalent yet. Okay? But that concept helps us to understand where the electrons in those bonds are spending their time. Right? That's it. So if we have a concept of electronegativity, we could now start to look at each of those bonds and say what happens. Right? Well, oxygen was the second most electronegative element. Okay? Fluorine's the first, so it's not hydrogen, which means what is oxygen doing to the electrons in those bonds? What does electronegativity mean? The ability to hold or steal bonding electrons. So if we push this to its utter extreme, oxygen, being more electronegative than hydrogen, is going to do what with the electrons? Take them away. Okay? It's also going to do it to the other one. And if we went through and calculated a formal charge on that atom, I know you didn't do it. Okay, you're not responsible for that. Right? What we would find is that oxygen would be negatively charged. Officially, it would be a -2 charge. Okay, that should sound familiar. That sounds kind of like oxygen's oxidation state. Okay? An oxidation state was dictated based off of electronegativity. Ooh, so they're all coming full circle. Okay, so if we're looking at that oxygen, we would expect it to draw all those electrons toward it. So we go, oh, I'm going to say the oxygen is negative. But if I say it's negative, I'm now saying it's formally negative, but it's not formally negative. Okay? So I want a notation that allows me to show that the oxygen is gaining those electrons. It's taking those electrons away, but not formally. So I still want the information of the negative, but I need to add something else to say that it's not actually a negative charge. The thing that we add is the thing that we mean for all changes. So if you've taken a physics class, you have changes, right? Changes in time, changes in distance, changes in temperature in a chem class even. What do we use to represent that change? What's the symbol? Delta. You're taking a math class and you do calculus, you do derivatives. It's frickin' delta. That just means change. So we could go through and we could use a delta. That just looks stupid. So we went through and used a lowercase delta, which also looks equally stupid for the record. Okay? But that's the notation we settled on. Okay? That delta symbol means partial. We are partially negative. Well, if the oxygen became partially negative, how did it do it? Taking electrons from the hydrogens, which means the hydrogens are now partially positive. And with that added context of my drawing of water, do I want those positive hydrogens to interact with my sodium ion? Just like when we put sodiums together, that was a bad idea. I don't want positive charges near each other. Okay? I don't want like charges near each other. I want the opposite charge near each other. So what should I go through and do? There's one option. Right? We know it was a really bad idea to put the positives next to the positives, so A must be wrong. Right? The next thing that we could go through and do as far as our picture goes, which is now going to look kind of stupid. I realized that turning it upside down isn't as cool as I thought it was. The positive is going to align with the negative. Just like it did with sodium bromide. Right? That interaction now explains the aqueous. It's describing what's happening at a molecular level with that phase. Right? So now we say, well, that's our relationship. Which of our answer choices closest matches that? Right? Well, A puts the sodium next to a positive hydrogen. That doesn't make sense. B puts the sodium next to the oxygen. What charge did we say the oxygen was? Negative. That's aligning the charges so that they cancel out. That's a good interaction. I like that interaction. What's happening with B? We're taking the negative of our bromide and we're aligning it with the negative of the oxygen. Do we want the same charges? Nope, that also doesn't make sense. Okay, because we've eliminated answer choice A and C, we know D doesn't make any sense. We like the option B, having those charges, which also means E doesn't make any sense. So what's the answer? C, of course. No, it's B. Just kidding. Okay. The fun thing about this that I really like is the description we just walked through. The thought process is what we do in organic chemistry. Right? It's what happens in biochemistry. It's what happens in all forms of chemistry. You're actually looking at the molecular level of what those atoms are doing and how they interact. And if they interact strongly enough, what happens? You make a chemical bond. You mean you do some chemistry? Yeah. Why the hell are we not talking about that instead of doing all this stupid conversion stuff? I don't know. Someone said conversions were more important, so we talked about that instead. Okay? That's actually getting into the chemistry side of it. That's neat. Make sense? Is that your question? Yeah. Questions about that or other concepts within it, or another question?
Because the positive goes to the negative, in a general situation, could the sodium and the bromide be on the same H2O molecule?
So could a sodium and a bromide interact with the same oxygen? Yeah. Or water molecule. Yes, theoretically. Okay. What you start to navigate into there is now probabilities. Okay. How much sodium bromide did you put into how much water? If you put a grain of sodium bromide into a massive vastly massive amount of water, the sodium ion and the bromide will immediately dissociate. Almost instantly, they're going to be pretty close. But over time, what they're going to do is diffuse through the whole pool, in which case they aren't talking to the same water molecule. But what if I add in more salt, and more salt, and more salt, and more salt? So you can put in a situation where the concentration of your salt is so high that, yes, they're talking to each other or talking to the same water molecule. You increase the probability of it happening.
Thank you.
Okay. Which, interestingly enough, pushes actually back to gases. Because when we consider gases, how much do our gas particles talk to each other? They don't. They don't talk to each other at all. Okay? To a first approximation, when we look at a gas, the volume, okay, our individual particles never actually see each other. There's open space in between. Okay? And because they're constantly moving around, okay, an individual gas particle, since it doesn't see any other particle, sees the entire volume as something it's accessible to. Which means it doesn't matter how much gas I put in there, they all see the exact same volume, which is counterintuitive to what we would think at a normal scale. When the first person moved into this room, they sat down, right? When the next person moves in, can they sit down in that chair? Gets a bit awkward, but no, they shouldn't, right? Because it was already occupied. Okay? And if we just said you can only sit for a second and then you have to get up and move around, okay? The more people we put in, eventually we start encountering these issues where the same people are fighting for the chairs. It's called musical chairs. Okay? That doesn't happen for gases when we consider gases at their simplest level, which is why when we look at gases, we get the fancy equation, Pibnert, PV equals nRT. That equation exists because we make some simplification to our understanding of gases. They never talk to each other. Okay? And it's that never talking that allows us to simplify those systems to come up with an expression that ballpark estimates most systems really well. Which is kind of important because the quiz asks questions, or the exam asks questions about what assumptions are being made with gases. So if that concept seems foreign to you, you should go back and review the video that talks about gases and those simplifications. Okay? Next question. We're going to interject with something else to potentially help with this solve. When we go through and write out all of our calculations, we push units, right? We get a measurement unit and we get a substance unit. Okay? Caffeine, that's a whole hell of a lot of letters. But at least it's less letters than C8H10N4O2, because that would be really painful to have to write out every time I try to deal with substance. Okay, so I'm just going to write out caffeine. But caffeine is still a whole hell of a lot of letters. Could I come up with a different symbol to represent caffeine? C, yeah. Okay. You could go through and just abbreviate your substance notation to be C. Okay. Perfectly acceptable. Okay. You could also go through and call it CAF. I personally would go with CAF, not C. Why would C be a bad idea from my perspective? That would be easy to get confused with carbon. Now, I'm not talking about carbon, I'm talking about caffeine. So I go, oh, well, I'll do Ca, but Ca could be confused with calcium, so that's where I would push all the way to CAF for my abbreviation. But again, you can pick anything you want as long as you don't get confused with your substance. So if we're going to look at this question, what are we being asked to solve for? Seconds of molecules. Oh, Lord have mercy, that's way too much. Right? Okay. I don't want to write that as I go through and solve. So what kind of simplification can I navigate through it? We talked through it, but I don't think I recorded it. We could turn the caffeine into CAF. Okay. We could convert molecules into MLC, and so we could keep that in there. Okay. And then Sagan's, we could go with SAG. Okay, that would be fine. Okay, I would actually make an argument, and I think there's a really strong argument, that we could actually abbreviate that as just SAG-CAF. Okay, and we'll come back to that one later, but for the moment, let's just stick with SAG molecule caffeine. Okay, so I need to solve for that. That's my unknown. I now need to talk about what I want to bring into this. Okay, I'm given a couple pieces of information. I'm given the grams of caffeine, and then I'm also given this weird conversion factor for what Sagans are. Okay? And everybody freaks out, I have no idea what Sagan is. We don't care. Okay? Remember, that's the point of the conversion process. You don't need to know what it is. Okay? Do you want to know what it is? Yeah? After we solve it. Okay? So, Sagan of things, 4 times 10 to the 9th things. Okay, so what do we want to start with? Do you want to bring in the grams of caffeine, or do you want to bring in this weird conversion factor? Weird conversion factor. Okay, why do you want to bring in the weird conversion factor first? Because I agree. Yeah, there it is. It's the unit we want. I want Sagan's molecules of caffeine. So how about I bring it in right away so that I've got that unit there? Okay, you don't have to, okay, but the point is just come up with a reason that works. So I know I have Sagan's of molecules of caffeine. That still just looks absurd to me, okay, but it's at least there. Okay, and what is that going to be related to? No numbers.
Oh, sorry. Molecules of caffeine.
It's going to be related to things. And this is the part that everybody freaks out at. Okay? And they go, well, what is things? Okay? I tell you to go to the store and buy a dozen. What are you buying? A dozen eggs. Okay? Or a dozen donuts. Could I tell you to go to the store and buy a dozen grams? That doesn't make any sense. A gram is a measurement. I'd have to take a measurement to figure out what that thing was. When we're talking about a dozen, you're talking about the thing that you are purchasing. So when we talk about this conversion factor, a Sagan of things equals a number of things, it's the object. I could have one Sagan of donuts. That would be really expensive. Okay? 4 times 10 to the 9th donuts. That's perfectly valid. I could go through and do that. Okay? The grocery store would be really upset. Okay? Or really happy because you're now buying tons of donuts for a long time. Okay? What is the thing in chemistry? A mole isn't a thing. A mole is a count of things. What's the thing? Molecules. Molecules are things in chemistry. What else are things in chemistry? Atoms are things in chemistry. Those are our things. Okay? And if we look at our conversion that we immediately wrote, Sagans of molecules of things, or Sagans of molecules of caffeine, we could immediately go up to our expression. It says Sagan of things. What do you think the things is? Molecules of caffeine. It's actually in the unit system that we've already written out. Okay? Which means the unit in the denominator is actually going to be the molecules of caffeine, including that substance. Now I need to bring in the numbers. Okay? If we didn't bring in the numbers, we didn't bring in the units, typically what I'll see students do is go, oh, well, I need to put 4.0, 10 to the 9th. Ignore the fact that we had sig figs. Okay? And they go, oh, well, it didn't work. Well, why did it not work? What unit did you put that next to? Well, I didn't write a unit. Yeah, you didn't write a unit, so you have no idea what you're attaching it to. If we backtrack through and follow the process that I've told you to do, look at the unit. Where does the 4.0 times 10 to the 9th show up? What is it next to? It's next to the things. What's our thing? Molecules. Which means 4.00 times 10 to the 9th shows up with our molecules in the denominator. The unit is telling us where to place it. Not some mystical formula that you may have memorized by accident by doing enough questions. Okay? What needs to show up next to Sagan's of molecules of caffeine? 1, why? Because in the expression, what shows up in front of Sagan's? 1. Use and leverage the information in front of you. Stop relying on chemical formulas. Or not chemical formulas, just mathematical formulas. Okay? Do we have our answer? No. What's the problem? I have molecules of caffeine. Do I want molecules of caffeine? No. So what has to happen? I need the molecules of caffeine to cancel, which means it has to appear in the numerator so that the units will cancel. Fantastic. Do I know the molecules of caffeine? This goes back to the question, does the question tell me the molecules of caffeine? No. Which means I got to do a conversion factor. Okay? What do I want to convert the molecules of caffeine to? Okay? We've got a lot of different options. Okay? I heard one option, we'll go with that one first. Grams of caffeine. Can I relate molecules to grams? How big is a molecule? Really, 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 really tiny, which means how big is the mass number going to be? Really, really, really tiny, which means that conversion factor isn't an easy thing to find. It's not found on the periodic table. Okay? That would have to be some bizarre conversion factor that you would have to look up, which means, does that one exist? No. Is there a different mass that you could bring in. Moles is not mass. We just did grams. The atomic mass unit. I could bring in the atomic mass unit. For those people writing that down, don't stop, because I would argue that's confusing, and I don't want you to memorize the periodic table. It tells you AMUs and molecules. I think that's a bad idea, because we want to avoid molecules as much as we possibly can. So let's not bring in another esoteric unit of AMUs. Okay? That is a valid conversion factor, and we can use that. It will absolutely work through this calculation, but it's going to require another conversion factor later on. Okay? So if you started the path with molecules to AMUs, I would recommend you have me look at your work and see if you followed that work through to a proper end. I don't think I want to write that one out, because the majority of the class didn't say grams or AMUs. The majority of the class said moles. Okay? So we want to convert to moles. Why? It's a conversion factor that you're aware of, so we just use it. Okay? Where do I find the conversion factor that relates molecules to moles? That is Avogadro's number. The periodic table is mass to moles. Okay? So I would have to have memorized Avogadro's number, 6.022 times 10 to the 23rd. Molecules or things, depending on how you want to address it. Molecule is our thing. So our 6.022 times 10 to the 23rd shows up with our molecules. What shows up with our moles? 1, because that's the definition of that term. That was something that you memorized or should memorize. Okay? I would argue you should memorize for the sake of doing these conversions and then never worry about ever again. Okay? Because the point of that number is that we never have to use that number. Okay? Now what happens? The molecules of caffeine cancel. Hooray! We're done? What's the problem? I have moles of caffeine. Do I want moles of caffeine in my answer? No, which means what do I got to do? I need a conversion, or not a conversion. I need to put in the moles of caffeine so that unit cancels out. Do I know the moles of caffeine? We go back to the question. Does the question tell me the moles of caffeine? No, which means what do you have to do? You're going to convert. What do you want to convert the moles of caffeine to? Okay. We could convert it to the grams of caffeine. Okay. That's known as the molar mass, and that is found on our periodic table. Irritatingly enough, it wasn't just given to you in the question, because that would have been nice.
186 grams.
Okay. A number was shouted out, 186 grams is equal to 1 mole. All right, do we get a second on that number? No, we're getting people not seconding that number, so I'm going to say the 186 was unfortunately wrong.
Is that all right?
No, 14, 4. That work looks good. 100. You got 154? 194.
Well, I
Yeah.
rounded up to whole numbers, not. I used decimal points.
Yeah, the decimal points shouldn't put it that far off, because those numbers are all pretty close, 12, 1. So without actually testing that addition. What am I hearing, 194? 194.22. Okay, we got at least 2 people, 3 people saying that, so I'm going to say it came in at 194, and you just missed something. Oh, yeah.
I can't believe it.
Yeah, neither can I. That's why we use a calculator. Okay, and hope that we can figure it out there. Okay, so now what happens? The moles of caffeine cancel. Am I done? No? What's wrong? I don't want the grams of caffeine. I need that to cancel out. Do I know the grams of caffeine? Yeah, that's given in the question, so I can say 0.0350 grams of caffeine. The grams of caffeine cancel. What goes in the denominator? 1, because I'm not relating it to anything else. This is just a straight given value. Technically a given measurement if we wanted to push at it. Okay. This was a given conversion factor. A given factor, we'll just call it. Okay, so now what do? Now I just do the math, punch it into the calculator. Okay? If you punch it into the calculator and get a number that has a power of 10, sitting at 30, 30 is probably close enough, 32-ish, more or less, you're not entering it into the calculator right. That's a calculator mistake. So 10 to the 32nd is going to be wrong. You're just not entering it into the calculator right. You've got to make sure you enter it in correctly. Okay, so if you're hitting that 10 to the 32nd, you can talk to me after class, and I can help you figure out how to use your calculator to ensure you don't make that mistake. All right? If we walk back through our conversions, the whole we didn't like the idea of dealing with molecules or actually just molecules, the 6.022 times 10 to the 23rd. It was a conversion factor that we used so that we never have to use it. Why are we using it here? To prove that you know how to deal with conversion factors that involve powers of 10. Okay? If I just asked how to solve for molecules, everybody would be grand and glorious, and it would be straightforward and easy. Oh, it's great and easy. Does that mean you actually knew how to do the conversion? Well, yeah, of course. Then when I ask Sagan's, why do you suck at solving it? Okay? What has happened is you've done enough questions where you're solving through for the number of molecules, okay, that all you've done is memorized the process, intentionally or not, on how to do that conversion. How do I know? Because I can throw in goofy-ass units and you fall apart, okay? And it's not just you. You throw this at a tutor, watch them crumble, okay? Because we very commonly just do things through rote process and assume we've learned. You haven't learned until you're forced painfully into that process. Okay? I feel bad for the tutors when they crumble with this, to be honest. Like I feel kind of sad. But at the same time, they need to know that what they're doing is also wrong. Okay? Kind of makes sense? If we go through and look at this, we could have said we could have just gotten away with Sagan's of caffeine. We didn't need to include the molecules. Okay? Why? Think about how we use our moles to molecules conversion, or even our moles. When we wrote out moles here, did anybody dispute and say, why didn't I write moles of molecules of caffeine? You just let that slide, didn't you? I didn't even realize that I did it. Okay? Because that's what that unit self-contains. By writing caffeine, we immediately imply the word molecule. Okay? But if we don't include it in our conversion explicitly for our goofy-ass Sagan's, okay, we fall apart because we don't know what thing is attached there, what measurement is there. And as soon as we drop that measurement in, if you're following the process, everything should kind of run smooth. Kind of make sense? Okay. I did say I was going to tell you what Sagan's were officially. I should look it up again just to make sure. Carl Sagan was a famous author who was also a very brilliant physicist and astronomer. And they invented the unit of Sagan's as a nod to him. And I believe what it is in reference to is the number of galaxies in the universe. I think is what it's supposed to be. I'd have to look it up. Like you could just Google it, and that's what it is. Okay. Questions about it? So it's not an entirely made-up unit by me. Who asked? Are we good? Whoever asked, are we good with it? Good. Did someone actually solve it all the way through so we can actually say what the answer was? You got B. Sounds like you said you got B. Did you solve it all the way? No. Did anybody else solve it? A couple people did? Okay. So yeah, we're hearing from at least 3 or 4 people that it should come out to be the magnitude of the power of 10 is correct. Okay, so that's reasonable. The rest of it is just going to be the numerics. When your calculator spits out E, that E just means 10. 10 to the power of whatever number comes after it. Okay, your calculator is going to give you a long run of numbers. We need to whittle it down to the appropriate sig figs. Is this question asking about sig figs? No. How do you know it's not asking about sig figs? Look at the multiple choice answers. Okay? Do any of those answers show a difference in the number of sig figs? That's how you know it's not a sig fig question. If you look at your answer choices, okay, for multiple choice, and you're seeing your answer choices are varying based off the number of sig figs, you should slow way the hell down and make sure you answer it according to sig figs. What if there were no answer choices? Sig figs is now an implied aspect of your question. The number that you come out, you have to make sure that you deal with the sig figs. Okay? But when you have the multiple choice in front of you, you're fine. Make sense? Next question. Okay, so we got 18 grams of rust produced when a 20-gram sample of iron is reacted with 8.59 grams of oxygen gas in a combination reaction. What is the percent yield of the rust? How do we calculate percent yield? Our actual over our theoretical times 100%. Do we know either of those numbers? And actually, let's backtrack a little bit on this. Let's get a little bit more specific on what we've written here. Okay? Because they're actually not asking just for blanket percent yield. We're asking for the percent yield of rust, which means we need the actual yield of rust. We need the theoretical yield of rust. That substance needs to appear in there. Okay? And then times our 100 would get this. Do we know any of those numbers?
Yes.
Yeah? What number do we know?
18 grams. The actual.
I totally phrased that wrong. You did a marvelous job answering that question. 18.0 grams of rust, okay, is produced. That's how much we actually got. That's what the question says. Right? Do we know the theoretical? There's a bunch of other numbers, right? Why don't we just bring in one of those other numbers? How about the 20? 18 divided by 20. That's a good yield.
No, it's iron.
And so for those people saying, no, we've got a good catch on this, that 20 isn't grams of rust. That 20 is grams of iron. That's not rust. I can't do that. Okay? Well, how about the 8.59? That's grams of oxygen. So neither of those are a theoretical yield of rust. So we're now in a bit of a dilemma. Okay? So if I have 20.0 grams of my iron, okay, I'm going to cheat and say my iron is Fe, which I think is a fair cheat. I think I'm allowed to do that. Okay, my 8.59 grams of oxygen, and I'm going to write O2 because it's diatomic. Okay, those are the other numbers I've got. To get this theoretical yield of rust, I need to do what with those numbers?
Would you combine with carbonation reaction?
I'll come back to you in a second. So keep your mouth shut. What should I do with those numbers? What am I trying to find? Theoretical yield would be the grams of rust. Right? Right? So what would I need to do? There's a hint. I've got some bread.
The limiting reaction.
I've got some cheese. And I got here a sandwich. So what do I need to go through and do? I would have to go through and convert those numbers, my 200 grams of iron and my 8.59 grams of oxygen, into grams of rust. Okay? And this is why this question is phrased here. It's put here in an awkward stance, so let's try and deal with that. How do I convert the grams of iron into the the grams of rust? What would I need to do? You want a mole ratio. Cool. Because I would need the moles of iron to convert into the moles of rust. Right? I need a mole ratio because I'm changing the substance. Awesome. I love that. Thank you. Right? Where do I find the conversion factor for a mole ratio? From a balanced chemical reaction, which means what do I need to write down? A balanced chemical reaction. So I take Fe and I react that with oxygen because those are my reactants, and I make rust. And rust is rust. What's the formula for rust? Okay. And this is where we can run into some interesting dilemmas. And so I like that you all went, okay, screech the brakes. I don't know what's going on with this. Okay. You said it's a combination. Combination means what do? We take the iron and the oxygen and we smash them together, which means the rust must be the combination of iron, Fe, and oxygen. But it's got to be a balanced chemical reaction. Someone mumbled something and I talked over you. It's got to be a balanced chemical reaction. Before I balance that chemical reaction, what must I do with my predicted product? I have to ensure that that predicted product balances the charges appropriately. What is the charge on oxygen? What is the charge on iron? Okay. So if we actually listen to the audience, we heard someone go +2, I heard a +3, and I heard very early on, I don't know, are you required to know the charge on rust? Sorry. Iron. No, you are not required to know the charge on iron. Why? Because it has lots of different charges. Okay? And if it has lots of different charges, do you know how much iron we need to balance the oxygen? We don't. Okay? Assuming it's +2 only works when we're looking at a single replacement reaction. This ain't single replacement. This is combination. Okay? And if that's the case, would I ever be able to figure out the mole ratio? So what could you do right now? Okay? One option, I'm just going to go through and erase everything. Don't frickin' erase anything. For the love of God, you spent some time to write something down. Okay? If you erase it all and then, heaven forbid, you moved on, which was a good strategy, okay? You just took all that work that I could be like, yeah, it's wrong, but you did some things. Like I can see a thought process here. Let me give you some points. You erase it all, what just happened? There's zero evidence that you've thought through anything at all. I can't give you anything. Okay? There's a few people that write heavily enough that when they erase, you can still see through what was written. Okay? And when you got back your exam, if you're one of those people, you usually see a big circle around it, and then usually me giving you some kind of points. Because what I'm trying to do is read the crap that you erased, okay, which was a bad idea, but I'm trying to give you credit for that thought process. Please stop erasing it. Don't make it harder for me to give you points. Okay, so don't erase. You need more paper? That's fine. Ask for more paper. Okay, but please don't ever erase. Okay, the point of the exam is to show what you know, not to show that you know it beautifully. Okay? So one option, yep, we just move on. Hell yeah, advance, I'm done. I stuck, doesn't make any sense to me. Okay? What you will see tutors going through and doing is saying, whoa, but Rust has the formula of, well, how did they know that? Fucking memorized it. That's not what you're allowed to do, so that doesn't work. Okay? So how could we possibly do this? Well, let's go back to another statement. Okay? This was a combination reaction. If I take 20.0 grams of the iron and 8.59 grams of the oxygen, how much iron oxide, how much rust should I make? How did you get 28.59 grams? You added them up. Why could you add them up? It's a combination reaction. Yeah. Why else can you just add them up? You can't say the same answer twice. That doesn't work.
The law of,
Yeah, yes. The law of
conservation
conservation of
of mass.
mass. Okay? That was one of the concepts that's addressed, the law of conservation of mass. So if we're starting with 28.59 grams of reactants, we should end with 28.59 grams of product. Okay? That's what I should end with. Because I should end with it, I might also call that a theoretical yield. Now what can I do? 28, I already forgot my number, 0.59 grams of rust. I take my 18.0, divide by 28.59 grams, multiply by 100, and I now have my percent yield. Okay. Since you gave me a number. Sorry, you said 62.96. 62.96. Okay, we are starting with 3 sig figs, it looks like, in all of our work, which means we get 3 sig figs, 6, 2, and the 9. Because the 6 is our first insignificant digit and is larger than 1, I have to add 1. By adding 1 to the 9, it becomes 10. I don't know, it adds another 1 to the next thing. Okay, and we get 63%. Make sense? Okay. Again, leverage the stuff you're supposed to know. So this question is a very tricky one in the respect of what are you supposed to know and what are you making assumptions on as you go through and solve. Okay? It's one that I'm very much on the fence on because if you don't know how to do it at all, what do you end up doing? No, you just add the two numbers together and you do the division and you get the credit for it. Okay? If you know something about conversions, you set up all that conversion stuff and go, oh, well, crap, I don't know how to do this. And so that person that knows something about the process loses credit. The person that knew nothing gets credit. And the person that knew a whole lot also gets it. It floats in a weird space. So definitely on the fence on this version of this type of question, because it's really trying to leverage that concept of conservation of mass.
If it was a decomposition reaction, we can't really figure that out because of the rate,
Right. How important was the information that it's a combination reaction? It's pretty flippin' important. Because if we look at any other chemical reaction, how many products do we produce? We get 2 or more. Okay? Conservation of mass just says the sum on both sides is the same. It doesn't say how much it divvies up. Okay? So because this is a combination, we're allowed to do this straight math. Okay? If we made it a decomposition, that's going to become a problem. Okay? We could go back and say how much did we start with. Okay? If we did a single replacement, double replacement, neutralization, or combustion, all of them have multiple reactants and multiple products. We can't run conservation of mass nicely with that. Okay? Which, I'm fairly certain, was directly addressed in the videos. Kind of makes sense? Whoever asked, are we good? I don't remember who asked, so. Oh, that was you. Are you good?
Is there another way that you could do that? Because I was doing percent yield. Because isn't it, like with other problems, isn't it actual moles and then over theoretical moles?
Okay, so when we look at this, it's actual rust or actual substance over theoretical substance. Okay, the critical part of that calculation is that it's the same unit. Okay, so in this case, we were in grams. Right? Could you do it in moles? Yeah.
Is it always, so it's not always moles?
It is not always moles. It is not always grams. It can be liters. It can be milliliters. It can be any measurement unit as long as it is the same measurement unit. That is the requirement. Measurement and substance must be the same. So when you're talking about doing that here, could you do that here? Can we convert this 28.59 grams into moles of rust? How would you convert it into moles of rust?
You have to know the balanced chemical equation.
we wouldn't need to know the balanced chemical equation. How do I convert 28.59 grams into moles? What would I need to do? Grams need to cancel, moles need to appear. Where do I find that conversion factor? Is that pointing at the periodic table? Yeah, okay, pointing at the periodic table, that's awesome. How many iron atoms are in rust? I don't know. And if you don't know the number of iron atoms, can you convert it into moles? No. So would you be able to use the moles for this? No, because you don't know that formula. Kind of, sort of? Other questions? Technically, we got 4 minutes. It's kind of like pulling teeth to get that other question. Yeah? What do we got? Real fast. So theoretical yield grams of aluminum serifs, you're putting the little hangers on it, of the aluminum iodide. We're starting with, where did it go? Well, that was fun. My vision just blurred. Grams of aluminum. Okay. Those two are different substances, so we're going to need a substance conversion. For me personally, I would launch straight into the substance conversion. So moles of aluminum need to become moles of the aluminum iodide. Where do I find that? Balanced chemical equation, which is really tiny up there, but 2 moles of the aluminum iodide become 2 moles of the aluminum. Okay. No units cancel, so that was kind of an annoying one to pick. Ooh, and now I'm getting lost in the serifs. Irritating. Moles of our aluminum. That comes from the periodic table. This was balanced chemical equation. Periodic table aluminum, I believe, is 27 and change. Close enough. 27 grams of aluminum. What happens with my units? My moles of aluminum will cancel. My grams of aluminum cancel. I wanted grams of aluminum iodide. So grams of my aluminum iodide. Moles of my aluminum iodide. Where do I find that conversion? That's, again, periodic table. I can't do that one in my head. Iodine is huge. Was at 127. Again, close enough. Times 3 plus your aluminum, which I said was 27. That number goes up here over 1. Our grams of aluminum, whoops, don't cancel. We wanted that. But the moles of the aluminum iodide would cancel, and I can now punch it into the calculator. I did that real fast just because we were real short on time there. Questions about what was up there?
No.
Okay. So again, you're tracking that unit process, and it's where you see what you want to navigate. Okay? Based off of the tutoring center and their advice, they typically start with your given information, your grams of aluminum, and what they reflex to is converting into moles. That's not wrong. It isn't. Perfectly fair game to go into moles. Okay? It's just choosing where you want to convert and why you're doing it. Why are they going to moles? Moles are kind of the central unit that allows you to branch out. So it makes the most sense to use that one. I'll stop.